Copyright in these lectures is either owned by the ANU or a third party who has licensed the ANU to use it. Students may use the recording for personal study only. No lecture may be communicated online, copied or shared without the prior permission of the ANU.
Okay, let's start today's lecture, and welcome to today's lecture. And it's also very hard for me to get up this early. And so first of all, some announcement about assignment 2. So basically, I have uploaded assignment 2, and the due date is next Wednesday, and 11 a.m. So no late submission. So that means you need to submit your assignment before 11 a.m. to the administrative office. Any questions about assignment 2? Any questions about assignment 1? Okay. So no questions, so let's just continue our topics. I think in the previous topic, we talked about multi-category response regression. So any questions about multi-category response regression? And one student asked a very good question, I think, on discussion forum, so we can have a look. So basically, you can have a look at it when you go back home. Basically, the student asked why more parameters, because in nominal regression model, we have more parameters. So maybe just look at my answer directly. So in nominal regression model, we have more parameters. So in this case, what I can say here is that more parameters never mean more accurate. Because if you still remember, I think in the variable selection lecture, we talk about usually when we have less variables or less parameters, those can lead to a better prediction without the overfitting problem. So usually more parameters in statistics usually lead to large variation, which is the opposite of the accuracy. So that's the reason why the nominal model usually has more parameters, so that means the nominal model has a larger variation compared to the ordinal model. And if you really have the information of the order, so my suggestion is to try the ordinal model first in order to involve that information in your modeling. But in practice, if we really have the ordinal data, intuitively the ordinal model should beat the nominal model. But in real data analysis, you actually need to compare the forecast performance of these two models. And you can actually get some intuition from some questions in assignment 2 to compare the forecast performance of the nominal model and also the ordinal model. So that's some question, I think, in the discussion forum, and I think this question is really good. Okay. So I think, yeah, more questions about the previous topic? Okay, if you do not have any questions, so let's just start this new topic, which is called logistic regression for binomial counts. So you will find that it has a new name, but it's actually not a very new topic. So you will find that we are still dealing with very similar data, but we just use another name to call the data type. And firstly, we are going to give a motivating example. So the example I think you should be very familiar with. So the example is about the advertising and the promotion. So that's actually from the binary logistic regression model. And then we are going to talk about this model, which is called logistic regression model for binomial counts. And then we are going to have something new compared to the binary logistic regression model, because when we have these binomial counts, we can actually perform model diagnostics. So that's something in multiple linear regression model, but we can also perform model diagnostics in this topic. And we are going to have these 3 plots. I think actually 2 plots and 1 test. And the first one is logit proportion versus explanatory variable plot. And if you remember the multiple linear regression model, we have the response versus explanatory variable plot. So you can compare. We have something similar here. And also, the number 2 diagnostic tools is called Pearson residual plot. And if you still remember, we actually have the student has a residual plot. For multiple linear regression model. So when you learn this part, my suggestion is just to compare these 2, and then you will find the idea is exactly the same. Okay, so let's just talk about our motivating example directly. So this example has been used in the binary logistic regression model. And here we consider that we have 30 customers, and a company gives a particular length of the advertising to these 30 customers. And then the company will see the response of the customers. So here, the response is that after the advertising, the customer is willing to buy the product or not. So because we have this whether or not as our response variable, so we define response equals to 1 if the customer was willing to buy, and 0 otherwise. So in this case, we have this binary response for the 30 customers. So that's the background of the data. And this is our data. So we have 30 customers. And we have different times of advertising, And for each length of advertising, we have our response. And for instance, we have 1, some customers are willing to buy the product. However, some other customers are not willing to buy the product. So that's our data set, and we have used that. And here, we give it a name. We call it a standard data form for this binary response. And then let's look at some terminologies to interpret this data, because later we are going to use these terminologies to help us to establish, actually it's not a new model, but it's a model by using these new terminologies. So firstly, we have something which is called trial. So what's the trial? So here we have 30 customers. So the 30 customers here correspond to 30 trials of this advertising experiment. So that means the company has these 30 trials of advertising to the 30 customers. So that's called, so here we just call this trials. We just use another name. And we consider different trials are independent. So that means the customers are independent. And then we define success. So what's the meaning for success here? Success just means if one trial is called success, so that means the customer is willing to buy, or equivalently, the response equals to 1. So let's just look at the data. So in the data, we have those ones as our success. And also, we can compute the number of success at the advertising time equals to 1.25. So the number of success at the time 1.25 is 1, 2, 3, 4, 5, 6. So the number of success at time 1.25 is 6. So if you see 1 here, so usually we just give it a name. So that means the success of this trial. And also we can have failure. So one trial is called failure if this trial the customer is not willing to buy. So, or I think equivalently, it means the response equals to 0. So this is the failure. And also we can compute the number of success. It here is not success, it's failure. At time equals to 1.25 is 1. And by using this tool, we can actually compute the number of trials. Remember, each customer corresponds to a trial. The number of trials at time equals to 1.25. Is 7, right? And also similarly, we can look at the other category for the value of time. So in this category, we have time equals to 1. So we can also compute the number of the success, which is 4. And also we can compute the number of the failure, which is 0. And the number of trials equals to 5. So for each category or each value of the time, we can actually compute the number of success, the number of failure, and also the number of trials. And also we can, because we have the fact success, so we can have the probability of success. So what's the meaning for probability of success? So basically, we are using the meaning of success to interpret the probability of success. Because success means response equals to 1, so probability of success just means the probability that the response equals to 1, or the probability that one customer is willing to buy in the trial. So remember that, so the probability of success just means, for instance, the probability that this one customer is willing to buy the product. Or you can consider in each row the probability that response equals to 1. So that's the meaning for this success, failure, and the trials. So if you still remember the binary logistic regression model, what is the binary logistic regression model? So in the binary logistic regression model, the probability of success is denoted by pi, and pi equals to the probability that y equals to 1, right? And in the binary logistic regression model, we actually use the, if you still remember, that is actually in the binary logistic model. We actually consider to use the logit pi. Logit is actually our link function equals to a linear combination of the explanatory variables. And the logit function is the link function, and logit u equals to u divided by 1 minus u, and we need to consider the logarithm. So that's the binary logistic regression model. And also in assignment 2, you're going to use this model to generate the binary response. So it's actually something we have learned, but we just consider to use some terminologies to rename the data set. And I think the most important names here is the number of success, the number of failure, and also the number of trials. So that's something new. And then let's look at, because we actually have a lot of repeated value of time, right? You can see we have a lot of repeated value of time. So a natural question here is that how about we aggregate the data by time? So how to do that? So I think I have showed some of the aggregation, I think, in the binary logistic regression model. So let's look at this in more details. So firstly, let's just try to use this tapply function. I think it's our second time, but I think you may be not very familiar with it. So I will explain it. So for this tapply function, so what's the meaning for this rho? So that means the sum of values of response by time. So that means we try to aggregate the values of response by time. So here you can see how to allocate those arguments in this function. Because we consider the sum, so we are going to have sum here. And also, we consider the sum of response, so we have the response argument here. And the last one is time. We consider to get the sum of the response by time. And if you look at the output, so you're going to have these two rows. The first row is actually the time, without any repeated values. So that means we actually have these 6 values of time. So that means the company only considers these 6 kinds of situation of the advertising time. And for each time, we have the sum of the response. So that is actually the, if you remember, that is actually the number of the success given each value of time. So for instance, given time 1.25, we have the number of the success equals to 6. So if you do not remember, you can look at the computation here. So the number of the success equals to 6. Given time 1.25. And also we can compute the other kinds of situation. So that is we have the 0, 0, 2, 2, 4. All of those numbers are number of success. And also we can compute the number of the trials. So what's the number of the trials? Basically the number of the customers here. And similarly, this tapply function returns the length of the response. By time. So basically that just means how many customers we have here given each value of time. So we also have two rows. The first row just means time, and the second row just means the number of the trials. And also, if you do not remember, so you can see at the value time value 1.25, we have 7 customers. So here, that's our computation by hand. We have 7 trials in this data set at value at time value 1.25. So basically, we just use the tapply function to help us to aggregate the data, and then we can define the aggregated data set. So how to do that? So firstly, we should have the time without repeated value. Without any repeated value. So this is the time. And how to do that, you need to use this function, to use the sort and unique function. So the unique function, basically, what's the meaning for the unique function? So basically, it returns time without repeated value. And also we use sort function because we need to consider the time from the smallest to the largest. To keep consistent with the rows here, if you look at the rows here, the time is from the smallest to the largest, and also the rows here from the smallest to the largest. So that's our first column to define time. And also we can compute the number of success, and we call it binomial count, the number of success, which is actually our binomial count. So this column is actually from here. And the last one is the number of the trials. The number of trials can be input in this way, and we call it total number. So in this case, we have this new data set, which is called aggregated data set. It's actually nothing new. You can consider it as the summary statistics of the previous table, of this table, right? By given different values of time. I do not think it's really difficult for you. So in this case, for each value of time, we do not have the binary case. We actually have some numbers. We have the binomial count, which means the number of the success. That just means the number of the customers that are willing to buy the product. So it's a number. It's actually from 0 to infinity, but I think the largest one here is 6. And also we have the total number. Total number just means the number of the trials given each value of time. So that's this aggregated data set. So why are we talking about this? Because in real data, sometimes we do not have the standard data form. We do not have this 0 and 1 data form. We do not have it. So in real practice, we do not have this data form. And usually, we have this data form. We have the aggregated data set. because obviously it's much easier for us to record. So usually in real data, so that means even if it's actually not that new, but we have some kind of new data form. So based on this new data form, we need to consider some modeling to deal with this new data form. And what's the feature in this new data form? So firstly, we have at specific value of explanatory variable, we have number of success. So that is the number of the customers that are willing to buy the product. So in this case, we call it binomial count, and we denote it by Z. And also we have the total number of trials. So that is the total number of customers given the specific length of the advertising, and we denote it by M. So that means we have the binomial count, Z, and also we have the total number M in the data. And also we have the explanatory variable time. So because here we actually observe some number or we call it count, so we need to consider to use some modeling to deal with this count variable or count response, and we call it binomial counts, the logistic regression model for binomial count, to deal with, to predict this number of success, or in other words, the number of the customers who are willing to buy the product. So here our target is different. We want to predict the number of the customers. So when we want to predict a number, we need to consider this binomial count regression model. But you will find that even if we try to predict this number, but we still need the number of the total trials. So that means the number of the total customers given this specific length of the advertising. So that means we actually need some extra information. So if we do not have this information, we cannot use this binomial count model. So that's the feature for this binomial count model, and we will discuss it more. So let's look at the standard form for the aggregated data, and I think I have explained it in the real data example. So we have the explanatory variable, we have the number of success, which is Z, and also we have the number of the trials, which is M. So that's the typical data set, and our purpose is to predict Z, but we need to consider that this M is actually known. The total number of trials is actually known. And remember that because we can define success and failure, we can also define one success in a trial, and we can define the probability of success, which is denoted by pi, in one trial. So I think in this data set, we have the M trials in this row, M trials, and we observe that success. And that's our observation of the data, but in the modeling, if you still remember the binary logistic regression model or the multi-category response regression model, we actually need to model the probability. So here we model the probability pi. Pi is the number of one success in these trials. And in this case, how to model this count Z? So obviously Z can only be from 0, so that means 0 success, 1 success, so on and so forth until M success, right? So Z is a number, and it can only take values from 0 to M. So if you still remember the, I think the 7055 or 1008. So how to use some distribution to model this kind of random variable, which can only take values from 0 to m, so which is the binomial distribution. So for the binomial distribution, we need to specify two. The first one is the number of the trials, and the second one is the probability of one success in a trial. So that's the how to represent the binomial distribution. But what's the binomial distribution? So the binomial distribution here is that the probability of z equals to some value. So the small z, the lowercase z is actually from 0 to m. So for instance, z can be 1. So z equals to 1. The probability of z equals to 1, or z equals to 2, and so on and so forth, can be represented by using this formula. And what I need to tell you here is this, the parenthesis mz. So what's the meaning? So basically it just means it's a combination number, and you can compute in this way. So it's just a formula. To describe the distribution of this random variable, which can only take values from 0 to m. So let's just try to consider a special case to help you understand this distribution. So let's consider m equals to 1. So that means we only have one total number of trials. And in this case, z can be equal to 0 or 1, right? Because that can only take value from 0 to m. And in this case, by using this formula, let's compute the probability that z equals to 1. So if you compute this, firstly, you need to compute this combination number, parenthesis 1, 1, and you will obtain 1. So you just plug in m equals to 1 and z equals to 1 here in this formula, and you will obtain 1. So it equals to 1 times the pi to the power 1, and 1 minus pi to the power 0. So that equals to pi. And also we can compute the probability that z equals to 0. So that is, that is still 1 times pi to the power 0, 1 minus pi to the power 1, which is equal to 1 minus pi. So what's the meaning here? So that means if m equals to 1, we are going to have the Bernoulli distribution. And hence, Bernoulli distribution is the special case of the binomial distribution. If you still remember, in binary logistic regression model, we have talked about it. So I think different arrow. So it's a special case. So basically, it just gives us a way to model the probability of the binomial count z, or the number of the success z. So that's the model part. So basically, we need to involve this in our modeling. And another observation here is that actually we can compute the proportion, which is not probability, which is proportion, because usually when we talk about proportion, it means something from the observation. So based on the observation, we can actually compute z divided by m, right? So z is the number of the success, and m is the total number. So basically, it just means the proportion of the success. And usually, this proportion can be used to estimate pi when m is very large. So just to remember this, we can actually use some proportion to estimate this probability of success. So I think this page is the most important page, I think, in today's lecture. Any questions? So remember this page, and then we are going to start modeling. So this is basically the purpose of today's lecture. So we have talked about a continuous response, two-category response, multi-category response, and then we are going to talk about the binomial count. And similarly, we can also model binomial count on the continuous and categorical explanatory variables. So I think that's something similar. And you can consider it as binomial count is actually the aggregated data form for the two-category Y. But the reason why we need to consider to use this binomial count is that in real practice, I think for most of the times we have this table instead of the 1-0 response data set. So that makes it convenient for us to use this aggregated data form directly. And another reason here is that it actually has more meanings, especially for this binomial count. And sometimes we are interested in predicting the number instead of 1 and 0 only. So in this case, we need to consider the binomial logistic regression model. So even though it's not that new, but it's still new in concepts, you can consider in this way. So let's look at how we model this binomial logistic regression model. So we have already talked about this binomial distribution. So what's the binomial distribution? Basically, this equation describes the binomial distribution. So that means we model the probability of each value of z by using this equation. So that's the binomial distribution. And the first assumption for this model here is that the response variable z, if you still remember z is the binomial count. So we model the binomial count as binomial distributed. So that just means that the probability can be expressed in this way. But we need to consider given some specific value of x. So if you will remember in our case, so that is the given some value of time of advertising. The response variable z is binomial distributed. So that's the binomial distribution part. And the m is actually our total number of trials. So you will find that in order to model this, we actually need m. So if we do not have m, we cannot have this probability. So that's the first assumption. The second assumption you should be familiar with. So that's the generalized linearity. So because in this model, what we do not know here is, I think m is observed. So the only thing we do not know is this pi. So we do not know pi. So the idea here is that we just model something we do not know by using the linear combination. So that's you can consider it as the spirit of the linear regression. Just model something we do not know by using the linear regression. And in this case, we need to consider to model pi by using this link function. The reason why we need to use the link function here is that because pi is actually the probability of success, so it can only take a value of 0 and 1. It's a probability. So, but on the other hand, on the right side of the equation, this linear combination, it can take value from infinity to minus infinity to plus infinity. So in this case, we have still have this mismatch problem. And I think in this case, what we need to do here is just to do something similar as in the binary logistic regression model to consider this link function to match the range of both sides of the equation. So I think that's the spirit of the generalized linear model. So if we have the mismatch of the range, then we just consider to use some link function. So here we use the logic link function, which is still the same. And then we have this generalized linearity. And you can compare it to the binary case. So the binary case is the G, the link function, the probability. I think I need to write more. The mu y given x. But for the binary case, because y can only take two values, 0 and 1, so this mean just equals to the probability that y equals to 1, which equals to beta 0 plus beta 1, x1 plus so on and so forth, plus beta k xk. So basically, this equation, you can consider it as very similar to the binary logistic regression model, but we have a little bit different interpretation for this probability of success. So that's the second assumption. And by using the second assumption, we can compute the inverse of the logic link, which is called logistic function. So that's the logistic function. And this function is in the range 0 and 1. So in this case, because we have the g pi equals to the beta 0 plus beta 1 x1 plus so on and so forth plus beta k xk, so pi just equals to the g inverse. So that's exactly from the modeling. And because the g inverse can only be in this range 0 and 1, so in this case, on the right side of the equation, we have the range 0 and 1. On the left side of the equation, we have also have the range 0 and 1 because it's a probability. So we have this match of both sides. So that's the spirit of the generalized linear model. So you can consider it as some review. So that's our modeling. The only thing we need to model here is this probability, because the only thing we do not know in the binomial distribution is the probability. And the last one is the independence. So what I need to remind you here is that we no longer have the response y. We actually have the response z. So given each value of the explanatory variable, we have the response variable, which is called z, and which also has a name binomial count. And also we have another observation m. M is the total number of the trials. So in this case, in order to distinguish the binary logistic regression model y, we consider to use z and m in this case to remind you that we are actually modeling something different. And also we consider m as the sample size. So let me explain it a little bit, because I think later you may feel a little bit confusing in your tutorial questions. So let's look at this real data. So the aggregated data form here is given each value of x, we have the value of z, and also we have the value of m. And in this case, so we have the 1, 2, 3, 4, 5, 6. So that means this is the Z1, Z2, Z3, Z4, Z5, Z6. And this is the M1, M2, M3, M4, M5, M6. So in this case, the sample size here equals to 6. So we use m, the lowercase m, to denote it. But if you remember the standard data form, this is the standard data form. So we use x and y to represent the standard data form. So for the standard data form, we have x1, x2, x3, x4, and so on and so forth until x30. And here we have y1 to y30. So in this case, we have the sample size. Here we use small n, the lowercase n equals to 30. So you need to be very careful about the notation here. Because when we have this aggregated data form, we actually have different sample size compared to the previous one. So my suggestion here is that just when you compute the sample size, just look at what kind of data it is. So if it's just this count data, so that means the aggregated data, just look at the sample size of this data and do not think about the standard data form. So when you have the standard data form, do not think about the aggregated data form, but just use this data form directly, because we actually have models for it. So if we have this standard data form, we actually have the binary model. Just use this model directly. And if we have the aggregated data form, we just use the binomial model directly. So that's easier for you. Binomial model. And do not need to consider the relationship between these two. And the reason why I talk about the relationship of these two here is actually to give you some motivation to consider this new model. But in real practice, just consider the data form directly and use the corresponding models. So any questions? Any questions about this data? So my suggestion here is that because we have this new model, so when we have the aggregated data form, do not need to think about the standard data form. Just use this model directly because it's more convenient. So that's the reason why I give this lecture. And because if you look at the modeling, so everything keeps very similar. So the only difference is this binomial distribution. So which is actually from the interpretation of the binomial count and also the total number of trials. And if we look at the generalized linearity, it's really similar. So the interpretation of this should be very similar to the binary logistic regression model. So I will not explain it. Just to use the odds, if you still remember. You can consider it as, because what's the meaning for pi? Pi is the probability of success, right? So what you can do here is just to, by using it, you can actually obtain the odds of success, which equals to pi divided by 1 minus pi, right? So that's the definition of odds. And if you do that, you can obtain this odds just equals to the exponential of beta 0 plus beta 1, x1 plus so on and so forth plus beta k xk. And the increase in x1 can be interpreted, can actually lead to the change of the odds of success by multiplicative factor of exponential of beta 1. So just to use it to explain your model, something similar to the binary logistic regression. And because after we can have the model assumptions. After we have all of those assumptions, we can actually obtain the likelihood. We can obtain the likelihood. So what's the likelihood? Likelihood is actually the probability that we observe these observations. You can consider in this way. So the probability that we observe Z1 to Zn. And then what you can do here is just to compute this probability. And because this probability depends on the parameters beta 0 and beta 1, which depends on beta 0 to beta k. So it's actually a function of beta 0 and beta k. So we usually just call it L beta 0 to beta k. So that's our likelihood function. And the next is just to maximize this likelihood function and obtain the maximum likelihood estimation. So here we obtain the beta 0 hat to beta k hat. And I will not derive in details because it's much more involved compared to the binary case. So I think if you can actually derive the likelihood of the binary case, it's actually beyond the scope of this course. So just understand that we can maximize this probability and obtain the maximum likelihood estimation. So because we still have the maximum likelihood estimation, so everything we have talked about in the inferential tools topic, if you still remember, we can use. So for instance, we can get the estimation, and also we can get the hypothesis testing, which is the z-test. We can have the z-test here, and also the p-value. And by using the estimation and also standard error, we can compute the confidence interval. So that's something similar. But in order to input the data in the modeling in this GLM function, so I need to explain a little bit more to you. So I think that's the end of the first part of today's lecture. I think it's the 10th week, so it's lecture 28. So let's take 10 minutes break, and then we are going to continue to talk about more details by using binomial logistic regression model in real data. Okay, let's start the second part. Any questions for this binomial logistic regression model? So basically, we develop this model only for the aggregated data form, because in real practice, usually we have the aggregated data form instead of the standard data form, because for the aggregated data form, it's much easier to record the data. So for instance, given some specific advertising time, 1.25, it's easier for us to record how many customers are willing to buy the product and how many customers are in the experiment. So that's the total number of the customers that are given a specific length of advertising. So that's much easier for us to record. And by implementing the binomial logistic regression model in real data, so firstly, we need to consider how to input the data in the GLM function. So in this specific case, what you need to do here is just to firstly use cbind function to combine the column of the binomial count and also the total number minus binomial count. So actually you need to involve the total number in the, you can consider it in the response. Why? Because the total number is also very important information. If we do not have this information, we can actually not implement the binomial logistic regression model. So input these two columns by using this cbind function. So that means combine these two columns by column. So you are going to have a two-column matrix. So that returns a two-column matrix. And the total number of information is included in this matrix. And the next is just to input this y here. So that's the only difference. So please be careful about this y here, because it contains the binomial count and also the total number of the trials. Both information are in this. And then the explanatory variable and the family is the binomial now, and also the link is logit, because we consider binomial logistic regression. And then we will have this table. And I think similarly we will have our maximum likelihood estimation, beta 0 hat and beta 1 hat. And also we have the corresponding standard error, the standard error of beta j hat. And also we have the z value. And also we have z value is just the estimation divided by, so which is our test statistic. And it equals to the beta j hat divided by the standard error of beta j hat. And also we have the corresponding p-value. So by using this p-value, we can test, for instance, here we can test beta 1 equals to 0. And if it's smaller than 0.05, we just reject this null hypothesis. And for the confidence interval, so the confidence interval is still very similar. So that is beta j hat minus plus z alpha divided by 2. So that's 1 minus alpha ci is times the standard error the standard error of beta j hat. So basically everything keeps very similar if you have this table. And the last thing I need to explain here is the residual deviance. So this is actually the deviance of the model. And if you still remember, the deviance just equals to minus 2 times the log likelihood value. So here we have the likelihood of beta 0 and beta 1, because we only have 2 parameters. So that's the deviance of the model with one explanatory variable time. And also we have the non-deviance. So what's the meaning for the non-deviance? So in order to explain the non-deviance, we need to look at this dropping deviance chi-square test. So I have mentioned to use the z-test to test beta 1 equals to 0, but similarly we can use the dropping deviance test to accomplish this task. So in order to do that, we need to know what's the reduced model, what's the full model. So when beta 1 equals to 0, so that means, because we only have one variable in this case, so that means the only thing left here is the intercept. So that's the reduced model, because beta 1 equals to 0. And in order to perform this test, the next is just to use this ANOVA function to compare the difference between the reduced model and also the full model and specify the chi-square test. And then you will obtain the two deviances. So the first deviance is the deviance of the full model. So this is the deviance of the full model, fit. And this is the deviance of the reduced model. So that is the model with the intercept only. So if you compare these two figures to the two figures here, so you will find that the first one is the residual deviance. And the second one is the non-deviance. So on page 15. So that means if you have this result, if you have this table of the summary output, you can actually use the non-deviance and the residual deviance to construct a dropping deviance test. I think that's actually some question in assignment 2. I think this part is similar to the dropping deviance test for the binary logistic regression model. And the test statistic is the difference of these two. And then you can compute the p-value. And here the p-value is smaller than 0.05, so we reject the null hypothesis and conclude that actually the advertising time variable is needed in the model. So that's the dropping deviance test, nothing new. And also, we can, by using the maximum likelihood estimation, we can actually obtain the fitted probability of success, because pi just means the probability of success. So if we plug in those beta estimation in the formula, we obtain the fitted value of the probability of success. And it is worth noting that if we consider this G function transformation, so what's G? G is actually our logit link function, which equals to log of u divided by 1 minus u. So if we consider this transformation of G, so we can obtain a linear combination. So that just means the logit transformation of the fitted probability should be on a straight line. And I will show it by using this real data example later. So this is the fitted value. So if x is from the training data set, we talk about fitted value. But if the x is from the test data set or from some new data set, we are talking about the prediction. So if you look at the formula for the prediction, the only difference here is that we just use some new value of x, and if we plug in those new values of x and also estimation of beta in, and then we obtain the predicted probability of success. So here we also can predict the probability. So let's look at how to use R to obtain the fitted probability. So here, if you still remember, fit is actually the GLM output. And if you use the fit dollar fitted values, you will find that in this specific model, the fit dollar fitted value obtain the fitted probability. So even though it's called fitted value, but actually it returns the fitted probabilities. And if we consider the logit transformation of the fitted probabilities, so that's the log fitted probability divided by 1 minus fitted probability. So that's the logit of the fitted probability as the y-axis. And also we have time as the x-axis, So in this case, we are going to have a straight line because that's our model. So our model is actually the logit of the probability equals to a linear combination. So we're going to have a straight line. So that's how we use this function, use this dollar to obtain the fitted probabilities. But we have talked about the fitted probability and also the predicted probability, but I think I use this example to explain the fitted probability. So let's look at how to obtain the predicted probability or the forecast of probability. So in this specific case, we may be interested in whether a customer is willing to buy if we consider this advertising time of 1.5 seconds. So what we need to do here is that, firstly, we define this new variable as 1.5, and the next is just to input this new variable in this data frame. And then we input this data frame in this predict function. I think that's kind of standard in this course. So always be careful when you use this predict function. And here you can specify the type equals to response. And finally, you will obtain the forecast of probability of success. So here, if we consider an advertising time of 1.5 seconds, the probability of success can be predicted by 0.98. So that means the customer is very likely to buy the product. So that's the probability of success. But if you still remember our original data set, we have the x, which is the explanatory variable, and z is actually the binomial count. So that is actually the number of success. That's something we actually want to predict. And also we have m is the total number of the trials. So naturally, I think it's totally enough for this data set to predict the probability only. We need to predict the predict the number of success. So that's our purpose. We need to predict the binomial count, the number of success. So in order to predict z, so remember that is actually from the binomial distribution, and the probability of z can be expressed in this way. So naturally, we can compute the mean of z. So what's the mean? Mean basically means the expectation of z. So how to compute it? You can use, because z can only take a value of 0 to m, so you can use 0 times the probability of z equals to 0, plus 1 times the probability z equals to 1, plus so on and so forth, plus m times the probability that z equals to m. So if you compute this mean, so this is the mean for the discrete random variable, and you will obtain that just plug in those probabilities. And then you can obtain this conclusion, which is simple. The mean here is actually m times pi. And because we can obtain the fitted value of pi, so we can obtain the fitted value of z, right? So this is the fitted value of z by plugging the fitted value of pi. So in this case, we actually have the fitted value of z. And because we have the fitted value of z, if you still remember, the only difference between the fitted value and also the prediction here is that if we use some new value of x, we are going to have the prediction of z. So let's just look at it. So in this specific case, we still consider the advertising time 1.5 seconds, but we consider for this specific value of the advertising time, we consider 5 customers in this experiment. So the total number of trials is 5. So we need to know this information in order to predict the number of the success, the number of the customers who are willing to buy the product. So in this case, we have some new value of m, so keep it here. And also we have so this is the, if you still remember, this is the forecast of probability of success. So which is pi hat. So if we use m times pi hat, which is actually the prediction of z. So this is the prediction of z. Because we use the mean, usually we use the mean to predict a variable. And in comparison, if you remember, the multiple linear regression model, we model the mean of response, and the prediction here, the prediction is just by using the estimation of the mean of response as the prediction. So similarly, we also use the estimation of the mean of response to estimate, to predict z. However, it's not an integer because z is actually a number. So roughly speaking, we can just round this value to an integer and then obtain 5, so which is roughly as the prediction of the response variable z. So that means for this kind of specific data, we kind of need more. We need to, I think probability is not enough. So we actually need to obtain the fitted value of the response variable z, which is actually the estimated mean of response z, in order to use the idea of it, and then we can obtain the prediction of z. So that's something different. So the probability is not enough. So any questions? I think the only new part may be here. The mean of the binomial response here is actually the total number times the probability pi. And for the other part, the idea to use this mean or the estimated mean as the prediction, I think is similar to the multiple linear regression model. So by using this fitted value of z, so let's look at some diagnostic tools. So I think the first one is not related to this fitted value, but the second one will. So firstly, let's look at the logit proportion versus explanatory variable plot. So this plot, in comparison, you need to compare this to in multiple linear regression model, the response versus the explanatory variable plot. So the idea for this plot is actually from the model, because in the model, we have the logit transformation of the probability of success falls on this linear function of the explanatory variable. So that's exactly the model. And also we have shown that this kind of linear relationship in the modeling, so this is actually from the model. So this is from the model. So it should be a straight line, because the model is actually the straight line. So if the model is true, so we should have this kind of observation. And remember that we actually have another kind of estimation of the probability pi. So what's the meaning for probability pi? Pi is actually the number, the probability of success. And here, because we have the number of success and also the total number, so the other estimation approach here is just to consider the estimation of pi here we consider to use another notation, which is the pi tilde. It's not pi hat. So the pi hat here is exactly equal to the G inverse beta 0 hat plus beta 1 hat x1 plus so on and so forth, beta k xk. So that's exactly from the model. But here we have a different method of estimation, which is the very straightforward estimation. And pi tilde just equals to z divided by n. So they are different. So this one is from the model. And this one is from intuition. You can consider in this way, because we use proportion to estimate the probability. So maybe from experience. So if the model is true, so that means these two should be very similar, right? If the model is not good, not okay, these two are going to be very different. So if these two are very similar, if the model is good, we should have this G proportion and X variable, and those X variable should have a linear relationship. So if the model is good, so that's the idea to plot a logit proportion versus explanatory variable, because G is the logit link function, and pi tilde is the proportion, and we just plot the G, pi tilde, and also X, and then we can obtain a plot. So this plot should show a straight line, otherwise the model assumption is violated. So if this is not a straight line, so you can just review the topic 4, even though it's for the response versus explanatory plot, but the ideas can be borrowed here to similarly solve this problem. For instance, by adding maybe x squared, by adding more x variables to solve this kind of problem. So I will not talk about here, but let's look at how to do that, how to draw a logit proportion versus the explanatory variable plot. So firstly, you need to compute the proportion. So the proportion is the binomial count divided by the total number. And secondly, recall that the G z divided by m equals to the log of the z divided by m divided by 1 minus z divided by m, because G is the logit function. And for this kind of function, because the log value here, the inside of this log function cannot be negative, So in this case, in this case, we need to deal with that, because sometimes z divided by m equals to 1, or sometimes z divided by m equals to 0 and 1. So that can happen in real practice. So if we have these two kinds of situation, the logarithm of 0 or the logarithm of the 1 divided by 0 does not have a definition. So in this case, we need to add or subtract a small quantity to the value 0 or 1 in order to make sure that we actually have this log value. So what we need to do here is that if the proportion, which equals to z divided by m equals to 0, then we just add some small quantity, which is 0.01. So you can define this small quantity by yourself. And I think in your tutorials, I think the tutor will talk about another way to define this small quantity to avoid the problem of log 0 or log 1 divided by 0 kind of situation. So this is to avoid log 0, and this is to avoid log 1 divided by 0, because these two do not have definitions. So if we do that, we obtain the proportion, and then we obtain the logit proportion. And what you need to do next is just to plot the logit proportion versus time. And then what you need to do is just to look at this plot to see whether or not it's in a straight line. Because here we do not have a lot of points. We only have 6 observations. So roughly speaking, I think it's on a straight line. So when we have more points, and we can basically make a more accurate conclusion. And because it's still similar to the response versus experimental variable plot, so what you can do here is just to review topic 4 to know more about how to use this plot to identify a linear relationship between the y-axis and also the x-axis. So any questions about this logit proportion versus experimental variable plot? So the difficult is just to compute the logit proportion. So I think you can have more practice in your tutorial. So let's just talk about another one. Another one is the Pearson residual plot. But in order to talk about the Pearson residual, we need to review a little bit about the student height residual for the multiple linear regression model. So that's another review. So for the multiple linear regression model, the difference between the response and also the fit value is called residual. And we can obtain the standard deviation of the residual. So the standard deviation of each residual equals to sigma times 1 square root of 1 minus hi. So what's sigma? Sigma is from the constant variance assumption. Which means the epsilon follows a normal distribution with mean 0 and and variance sigma square. And what is hi? Hi is actually our leverage. And the leverage is used to identify the observations with distant experimental variable values. So if you do not remember it, just review it in the lecture notes. So what's the leverage? So in this case, we can compute the standard deviation. And because the sigma is unknown, so actually we need to use the standard error by using the estimation of sigma. So this is the estimation of sigma. And in this case, if we consider the residual divided by the standard error of residuals, which is the standard version of the residual, we call it the student height residual. So the reason why we do that is to look at the residuals on the same scale by dividing this standard error. And in this case, we have this conclusion that the student height residual are roughly standard normal distributed with the mean 0 and variance 1. So if all of those assumptions are satisfied, we should have this conclusion for the student height residual. So that's the review part. So now let's just look at how to use this idea, borrow this idea from the multiple linear regression and look at the Pearson residual for the binomial count. So Pearson residual, you can consider it as the name for the standardized residual in the binomial logistic regression model. So it's just a name, but the idea is very similar. And recall that earlier we defined the fitted value of z. So what's the fitted value of z? So that is actually the mu hat zi given xi. And that equals to the mi times the pi hat, the probability of success. So I think we should still have I, because for different x we have different probability. So by using the fitted probability, we can compute the fitted value of z. So in this case, we can also define some residual. and the residual is the difference between the binomial count and also the fitted value of z. And in this case, we can still obtain the standard deviation. So here, the standard deviation is equal to mi times pi I times 1 minus pi I, and then square root. So how does it come from? So if you still remember, z is from the binomial distribution of n and pi, and we can obtain the mean of z is m pi, and actually the variance of z is m times pi times 1 minus pi. So it's actually from here. So you can obtain the standard deviation of residual also equals to this mi times pi I times 1 minus pi I. And because pi I is unknown in this case, pi I is the probability of success. So in order to obtain the standard error, we need to consider to plug in the fitted value of pi, which is pi I hat. So this is the pi I hat, the fitted value, by plugging the value of x and also the value of the estimation. And you can see, because the value of x depends on I, so this pi also depends on I. For different observation of x, we will have a different probability. And this Pearson residual can be computed by using this standardization idea. So that's the residual divided by the standard error. Something similar here, but we give it another name, which is called the Pearson residual. And similarly, because we consider the denominator as the standard error, so we just want to look at those residuals on a same scale. And also we have the similar conclusion. So if we have a large value of mi, so usually we need m is larger than 5, then these residuals are roughly standard normal distributed. So if the model assumptions are satisfied, we'll have this approximately normal distributed. So if we have this approximately normal distributed, so if you still remember the nature of the normal distribution, most values of the normal distribution concentrate on the middle of in the middle of 0. So in this case, if this residual falls into the two tails of the normal distribution, and in this specific case, we consider when this the Pearson residual is larger than the 97.5% quantile or smaller than the 2.5% quantile, and then we say this Pearson residuals fall into the two tails of the standard normal distribution, and in this case, it's too large because most values concentrate in the middle. So in that case, we will doubt that this observation is an outlier. So we can use the Pearson residual to identify the outlier for the binomial logistic regression model. So I think I just copied this page from the student has residual. The standard is basically the same. So the only difference here is just how to construct this Pearson residual based on the idea of the student has residual. And let's just look at how to obtain the Pearson residual by using R. I think it's not hard. So what you need to do here is just to use this GRM function output, and also you need to input the type equals to Pearson. So in that case, you are going to have the Pearson residuals. So that's the Pearson residuals. And if you use this plot, and you will obtain the Pearson residuals. And also you can use this AB line function to plot the cutoff. The cutoff is the 1.96 and minus 1.96. Basically, those cutoffs are out of range of this plot. You can see out of the range. So in this case, the plot will not show these cutoffs. And obviously, because here we only have 6 points, 6 observations, so these 6 observations are within this range. So in this case, we do not have the outlier problem, because we have 2 small number of the observations. Any questions? So it's not hard to implement it in R, and I think the only difficult part is how to obtain the standard error of the residual for the binomial count. Any questions? Okay, I think in the end, I'm going to talk about this test. So this test is actually very important. I'm going to slow down, because it's called the deviance goodness of fit test. So I think in the beginning, you may just be confused of this test with the dropping deviance test. So what's the dropping deviance test? So let's look at this case. So even if we both have this deviance in the name in the test, but they actually test different kind of things. So for this dropping deviance chi-square test, we have the test of the coefficients, basically. So in this specific case, we test beta 1 equals to 0, or if we have more variables, we can test beta 1 equals to beta 2 equals to beta 4 equals to 0. So the dropping deviance test is used to test the coefficients. And usually we can call those beta coefficients or regression coefficients or regression parameters. But the deviance goodness of fit test is used to test the model. It's not used to test the coefficients. So what's the null hypothesis? What's the alternative hypothesis? The null hypothesis here is that the model is actually appropriate, or the model is accurate, the model is good. And the alternative hypothesis is the model is not appropriate. So they are totally different. One is used to test the model, and the other is used to test the coefficients. So what's the meaning here? So you can consider here for the dropping deviance test, it implicitly assumes that the model is actually good, and then we test the coefficients. So in order to perform this dropping deviance test, firstly, we consider the model assumptions hold, and then we perform this test. So remember, all the hypothesis testing, confidence interval, all the inferential tools are only valid when all the assumptions are satisfied. If those assumptions are violated, if you still remember, we can actually not do this hypothesis testing. So in this case, we actually assume the model are good, the model is good, and then we consider to perform this dropping deviance test. So before we do this dropping deviance test, we actually need the model diagnostics. So the logic here is that we need to do the model diagnostic first to check the assumptions. So if the assumptions is good, then we can perform the inference, including the hypothesis testing, confidence interval, and everything. So if the assumptions are not satisfied, we cannot do that. So in order to perform the model diagnostics, the third step is to perform this deviance goodness of fit test. So it is used to test whether or not the assumptions or the model is good. And the next thing, if the model is good, we can use the dropping deviance test. So that's the difference between these tests. So they are actually dealing with different problems. So the deviance goodness of fit test is used to test whether or not the assumptions is satisfied or whether or not the model is good. So how to do that? in order to perform this test, we need to compute the test statistic, which is the deviance. So which is exactly the deviance. We do not need to consider the dropping deviance. And this deviance should be compared to a chi-square distribution. So the distribution is still chi-square, but we have the number of the degree of freedom m minus k minus 1. So m is actually the, if you still remember, m is the sample size. But it's the sample size for the aggregated data. And what's k? K is the number of the explanatory variables. And then we can compute the p-value. So that's the formula for the p-value. So basically, this test is different. So just remember. And let's look at how to, in our real example, how to perform this goodness of fit test. So firstly, you can use the summary output to obtain the deviance. So this is our deviance of model, and which is our test statistic, right? And then we need to obtain we should compare it to the chi-square distribution, m minus k minus 1. So what's m? M in this case equals to 6, because we have 6 observations. So just to review the previous pages to see how many observations we have. And what's the number of k? K is actually the number of the variables. So because we only have one variable, so k equals to 1. So m minus k minus 1 here is 6 minus 1 minus 1 equals to 4. So we need to compare to the chi-square distribution with the number of the degree of freedom 4. So how to do that? So firstly, you can obtain the deviance. So that's the test statistic. And that's the number of the degree of freedom. So m minus k minus 1, which equals to 4. And you can also see this number of the degree of freedom also appears here. So that makes everything a little bit easier. So what you need to do here is just you can look at this table and obtain the test statistic and the number of the degree of freedom, or you can use this dollar of the summary output to obtain the deviance and also the number of the degree of freedom. And the next thing is just to compute the p-value. So what's the p-value? The formula is in the previous page, but we can just write down the formula here. The formula here, the p-value here is the probability that some random variable is larger than the test statistic. And this random variable S follows a chi-square distribution with the number of the degree m minus k minus 1. So that's the p-value. So that's the formula for the p-value. But in order to compute it, basically we need to use R. And when we use R, usually it's easier to obtain the probability that is smaller or equal to instead of the larger one. So by using this formula, we can just put 1 here. And the probability for this chi-square distribution is smaller or equal to the test statistic. So what you need to do here is just to use this probability of chi-square distribution function, and then just input the test statistic, which is the deviance, and the number of the degree of freedom, which is m minus k minus 1. So this, I think, is the only case, I think, in this course we need to use a formula by ourselves to compute the p-value. So after we compute this p-value, we have this result that this is larger than 0.05, so we cannot reject the null hypothesis. We cannot reject the null hypothesis, but what is the null hypothesis? So that means we cannot reject this model. So if we cannot reject this model, we have this conclusion that no evidence this model is inappropriate. So please be careful here. I have already mentioned we can never accept the null hypothesis. So that means we can never say the model is appropriate. We can only see that there is no evidence the model is inappropriate. So you can only say that because we just do not have evidence to reject the model. So if you say the model is appropriate in your final exam, definitely you will get 0. So please be careful here. I think the case here is that because we only have 6 observations, so usually when we say we have no evidence, so sometimes we mean we do not have enough observations to actually to detect the violation of the assumptions. So that's how we use this test. And I think it's the end of today's lecture. And any questions about this test or about the other material in this binomial logistic regression model? And I think it's the end of this model. And in the next lecture, we are going to talk about Poisson-Count regression model.
Just like the overall significance testing MLR?
No. So for I think the student asked about this question. So is this deviance goodness of fit test is the same as the overall significance test in R? So if you still remember the overall significance test, what's the meaning for the overall significance test? It's actually a special case of the chi-square dropping deviance chi-square test, remember? So the testing of the overall significance here is just to use the, if we look at the table, the overall significance test is just to use these 2 values to obtain a test. So which, in this case, just means we are testing beta 1 equals to 0. So what's the meaning for testing beta 1 equals to 0? So that just means that firstly, we consider the model assumptions hold, and then we test the beta 1 equals to 0. Whether or not this variable is needed in the model, you can consider in this way. I think in more general overall